Let me introduce our first speaker, who is Bryan Lynn. So Bryan was born the son of a commercial tuna fisherman. He grew up in Puerto Rico. He received both his undergraduate and PhD degree from Columbia University. His thesis was the first complete high-precision Electroweak one-loop calculation of corrections to parity violation in atoms. He then went on to a postdoc at ICTP with Abdus Salam, followed by postdocs at the University of Oxford and at SLAC, where he focused on the physics of electron-positron colliders. And he then joined Stanford University as physics faculty in 1986. When the superconducting super collider was canceled, he quit physics in disgust and moved off to Wall Street to finance, working in New York and London in derivatives trading. Bryan strongly contends that physicists were responsible for saving the world from the financial collapse of 2008 through their work in derivatives markets. He retired in 2009 after a career in finance as managing director at Merrill Lynch, global head of quantitative risk, and global head of foreign exchange risk management. And he then came back to theoretical physics, and he's now a visiting professor of physics here at Case Western and a senior research associate at University College London. His research focuses on new, surprising, and unanticipated properties of the spontaneously broken standard model. So unfortunately, Bryan is ill and could not make it today, so Michael Peskin has kindly agreed to fill in and give his talk for him.
Okay, well, good morning. It's quite an honor to be at this symposium, so I thank you very much to the organizers for inviting me. Actually, this is not my talk. My talk is the next one, but I was asked to give this talk in place of Bryan, and so there's a disclaimer that I need to publish right away, which is that Bryan was supposed to give this talk on the history of the theory of precision electroweak interactions, and he, as I said, he's ill. He had to cancel at the last minute. He said, "Michael, here's all my stuff, just put it together." What it turned out to be was a bibliography of 1,008 items. So instead, I'm going to give an kind of impressionistic version of this history. Hopefully it will be a well-told story, at least I hope so. It will not contain all the references, so if I didn't refer to your paper or your colleague's paper, please excuse me. I did ask the organizers of this conference to put Bryan's and Robin Stewart's article on the Indico page, so you can read it there. And there's some cases where I differ a little in the interpretation, so you can see exactly what Bryan meant to say if you look there. So now let's talk about this subject of precision electroweak theory. The precision electroweak theory actually begins before Electroweak. It really begins with a paper by Toichiro Kinoshita and Alberto Serlin, which was written just after the proposal of the V-A theory, and I think maybe even before that theory was actually published, when it was still in the form of the left-handed neutrino hypotheses. These guys were interested in radiative corrections. They wanted to make the theory more precise for the case of muon decay, and so they wanted to investigate what radiative corrections would do to muon decay. The work is really classic because it involves the emission of a photon in muon decay, the logarithmic divergences in the infrared, which then they were able to show how they cancel. There are also, however, logarithmic divergences in the ultraviolet that they were not able to control, because at that time there was only the four Fermi theory, which was not really a fundamental theory of weak interactions. And so this beautiful work kind of languished for a while. It was used in all the subsequent analyses of muon decay, but it wasn't somehow the complete story. Actually, I learned at breakfast today that the first people to do this calculation within the Weinberg-Salam model, just after the Toft and Veltman paper, were Helen Quinn, Joel Premack, and Tom Appelquist. But in any event, one had this level of precision back in the 50s and 60s, but after the standard model of weak interactions was established, one had to go forward and do something better. And so, in particular, after the invention of the SU2 cross U1 gauge theory, the successful renormalization, and the order 1 vindication of this theory by experiment, Tini Veltman and Alberto Serlin again picked up the thread. Can we really do precise calculations that then can be tests of the theory? There are two very important developments that happened at this stage. First, in the mid-70s, Veltman had the vision that one could actually master the whole complicated technical art of one-loop calculation in this theory. So this is a theory which was considerably more complicated than quantum electrodynamics or even quantum chromodynamics. A very large number of diagrams involving a diverse array of massive particles. One needed a complete technology for one-loop Feynman integrals, and he proceeded to develop it. There were some difficulties. The box diagram integrals were a little hard. He had to enlist some former student of his named Gerard Toft, maybe, as I say, not necessarily gainfully employed in this era. And so they executed these integrals, and they presented a complete program for one-loop calculation. Now, the landmark is the 1987 paper of Passarino and Veltman, which then did a complete calculation of E plus E minus to mu plus mu minus within this theory, using the new technology and basically expanding it to be able to calculate systematically evaluate all of the many diagrams that are involved in this theory. That paper also introduced a technology for the reduction of one-loop integrals, which is actually still in use today for precision calculations at the LHC. And probably it's worth pointing out that in the 2000s, there was another twist on these methods. Some new ideas came into the game by Byrne, Dixon, Dunbar, and Kossauer, and Asola, Pitau, and Papadopoulos, among many other people, I should say, that allowed multi-leg calculations. And so Passarino-Veltman plus this new set of ideas based on unitarity now allows one to do calculations at the LHC like QQ bar goes to 5 gluons and a W boson. It's really quite impressive. Maybe what's even more impressive is that Veltman very early saw that this technology would eventually be susceptible to automation. And that is actually now achieved in codes like the one I mentioned here, MadGraph 5 at AMC at NLO. Those of you who are curious, download this thing and run it. It's really amazing. And it now puts precise one-loop calculations in the hands of experimentalists as well as theorists. The other development that I'd like to discuss is the crucial one of Alberto Serlin and Bill Marciano. Serlin had the idea of completing the radiative corrections to the electroweak theory. I think Marciano was more interested in the precise predictions of, at that time, the new hot thing, the SU5 grand unified theory. And they did calculations that controlled the threshold behavior both at the weak scale and at the gut scale. In the process, they introduced some very important concept that I'd like to discuss here. So weak interaction theory basically has 3 parameters. This is not functioning. The middle, oh, this? Okay, 3 parameters, G, G prime, the SU2 and U1 couplings, and V, the vacuum expectation value, or alternatively, the mass scale of W and Z. Marciano and Serlin suggested that one could tame the process of renormalizing the theory by concentrating on a set of 3 observables, on-shell observables that would replace these quantities. And the ones they suggested were alpha, G Fermi, and sine squared theta W defined in this way as 1 minus MW squared over MZ squared. So basically, you compute the one-loop diagrams with their divergences. you insist on the physical values of these three quantities. That basically carries out the renormalization on these quantities. And then the rest, you're home free. You can now calculate anything you want. A very simple but very beautiful concept, and they carried this out for many processes, including the W and Z masses, neutrino scattering, etc. Maybe I should say in the process, they discovered that there's a very large one-loop correction, about 5% in MW squared, due to the fact that the QED constant runs from the familiar value of 137 to a value of about 129 at the W scale. It's a large shift, and it basically affects very strongly many of the properties. This is one of two relatively large effects in precision electroweak calculation that really affects it quantitatively. Everything else is going to be the kind of high precision tests to many significant figures. Maybe I should say a little more about this statement of three on-shell quantities. Electroweak theory, as I said, requires three renormalizations for three parameters, but there's a great deal of freedom in how you do that. Nowadays, I guess it's common following the particle data book to use MS-bar, but all the original calculations were done using an on-shell renormalization of one kind or another. And basically, you can relate that all so you want to use alpha and G Fermi, which are the two extremely well-measured anchors for the theory. And the third one you can take to be sine squared theta W. Now, there are many possible definitions of sine squared theta W in terms of experimental observables. These definitions all agree at the tree level, and they differ in one-loop calculations. The equality of two definitions is something called a tree-level natural relation. So this is a technical term in a spontaneously broken unified theory, unified renormalizable quantum field theory. If you have two quantities that agree at the tree level and differ only by radiative corrections, that difference is finite. It requires no further renormalization, and therefore it's a prediction, a testable in principle prediction of the theory. For example, Marciano and Serlin define sine squared theta W through this relation. Cosine squared theta W is mw squared over mz squared. Other people, especially at the time that the Z resonance was studied experimentally, thought you should take the three best measured observables in this era, alpha, G Fermi, and mz squared, combine those to a model sine squared theta defined by this formula, and then you get a different definition. These two differ by a finite amount, which you can compute unambiguously. Similarly, if you're interested in the physics of the Z, and in particular the parity asymmetries, you might want to use the leptonic parity asymmetry, which is given by this formula, as the definition of sine squared theta W. So this formula would be exact with this sine squared theta W star in here. And again, the differences between these quantities would be computable, and they would be tests of the theory. So this is a very important idea. Actually, Bryan Lynn, in his work, extended this idea by defining a running sine squared theta W star of q squared, so that basically you compute this with some effort, and then beyond this, the corrections basically are at the tenths percent level, and then you can begin to fill in the rest of the theory. Very good. So now I guess we have to talk about the interface with experiment. It was clear already in the 70s, and actually the motivation for the creation of these accelerators, that a wonderful way to test this theory, really put it to an extreme test, is to produce the Z as a resonance in E plus E minus annihilation, make individual Z's in the laboratory, hopefully a very large number of them, and then try to study their decays and angular distributions in great detail. And this was the work of the accelerators LEP at CERN and SLC at SLAC, which were basically designed to carry out this program. Now, in order to put everything together, there was one new ingredient that was needed. Namely, if the Z is a resonance, as in atomic physics, you would like to understand the Z line shape. And actually, the theory of the Z line shape is quite complicated, because if you radiate photons from the initial electrons, you distort that line shape. This is an order 1 effect, and it affects what you will actually see in experiment. Here are the estimates for that. The quantity beta here is the usual measure of the strength of initial state radiation. It contains a logarithm of S over me squared multiplying the alpha. It's equal to 0.1 at S at the mass of the Z. But also, the Z is narrow. So it's easy for a photon to take you off resonance and then distort the shape of the resonance. That effect is given by this parametrically, beta times the log of mz over gamma z. That number is 40%, which means that the Z is going to be, the shape of the Z resonance is going to be qualitatively shifted by initial state radiation. And then if you want a precise calculation, you have to basically do the 0th order result and then correct it to higher loop order. The way to do that was pointed out in the mid-'80s by these people, Victor Fadin and Valerie Jose, who built a very beautiful formalism in which they regard photons and electrons colliding in the Z experiments as partons of the electron. So you can write some Altorelli-Parisi equations, which begin with an elementary electron, then emit photons gradually, and then eventually the final electrons are annihilating to produce the resonance line shape. This concept was then improved by various people with another 2 loops of calculation to give a theory precise to the 0.1% level. After this, there was, of course, the hard work of actually carrying out the program that these people had set out, trying to look at each individual process, supply computations for all the aspects of Z physics. So here's the place where I'm really going to fail. There's no way that I can organize for you and explain who did what and the various contributions. I'd like to put up here the names of some people who really made essential contributions to this part of the effort. Dima Bardin in Russia, Fritz Behrens, and Ronald Kleiss, who were the experts at that time on ordinary QED radiative corrections. Bohm, Denner, and Holleck, who really dug into the W exchange part of the diagrams. Fred Jaegerleiner, Luca Trentadue, who did very beautiful higher loop work on the Z line shape, and Tord Riemann, maybe I should have said Bardin's collaborator in the Eastern European aspects of this. Actually, there's one person who deserves a picture, but not because he did any really difficult calculation. Of course, he was already known for essentially state-of-the-art calculations in QCD. But Altorelli played a crucial role here in basically being the person who ensured that every calculation that should be done for the LEP SLC program was done. So he cracked the whip on the theory community. He created this famous yellow book, Z Physics at LEP 1, 1989, and in that way put together essentially the complete set of calculations that experimenters would need to do the experiments. One more contribution that I would like to highlight, the interface between that book and actual experimentation is done by event generators. And there are 2 event generators that were extremely influential through the program of the LEP measurements. One is called ZFitter. It was put together by an Eastern European group that you see here. Tord Riemann, Sabina Riemann, Dima Bardin, the leaders of this calculation. The other called Carl Z, and there are various versions of that followed, put together by Stanislav Yadok and Benny Ward. And I think we'll hear a lot more about this in Benny's talk. Okay. Now, Alain Blondel tomorrow will tell you about the experiments. But please excuse me, I just can't resist showing you a few of the results that were obtained in the experimental program and their connection to this theory. There are many beautiful tricks in the experimental program that I do not have time to describe, but hopefully Alain will discuss those tomorrow. Here I'd like to concentrate on the main physics results. So remember I told you that tremendous attention was paid to the theory of the Z line shape. So here is actually a measurement of the Z line shape by the Opal experiment at LEP. People in the first row, well, maybe Jerome's eyesight is not so good, can tell that there are error bars on these points. This is a 0.1% comparison of experiment going through the resonance with theory. Please notice that the resonance is asymmetric. That's due to the initial state radiation effect that I discussed with you. Actually, this line shape is a one-parameter theory. Once you know the position of the Z resonance and actually the value of alpha S, you can compute the rest of it if you're sufficiently strong. It includes all three of the fundamental interactions, electromagnetic, weak, and strong. Strong coming in through the width of the Z, which is predicted by this theory. Here's the official LEP summary of these calculations. So this is the composite of the 4 LEP experiments. This curve is very nice because it shows the 0th order Z line shape here and the actual Z line shape distorted by initial state radiation. The error bars are actually increased by a factor of 10 so that you can see them in this picture. It's really an amazing result. In general, the various classes of Z decays are very cleanly separable from one another. Electron, muon, tau, you see the 1:3 topology here. This is a 2-jet event, which would correspond to the quarks. And then one can look at all the branching ratios of the Z that are predicted by this experiment. There's one that I should call attention to in particular, which is the decay Z to BB bar. The B actually, it is a light quark, but the B left also lives in the same multiplet as the top quark. And so it's partially a heavy quark. And in particular, beyond all the radiative corrections that we've talked about so far, there are these diagrams which actually correct the Z width to BB bar in a way proportional to the top quark mass. It was pointed out by this group of people, including Barden and Riemann, that actually this correction is enhanced by mt squared over mw squared. So it's an exceptionally large radiative correction. It turns out to be a -2% correction in this ratio of Z to BB bar over Z to all hadrons. I'll show you the number later, but let's just say this ratio was measured to 0.5% by the LEP experiments. And it turns out that this correction is absolutely necessary in order to have good agreement between theory and experiment. Another aspect of the Z profile is the presence of parity asymmetries. The Z is part of the weak interactions, it's parity violating, and therefore it decays more strongly to left-handed particles than to right-handed particles. And you can measure this in a wide variety of ways. Something that I like very much about this is that the same value of sine squared theta w, when you put the couplings into this formula, give you very different answers for the different types of standard model matter. The asymmetry is 15% for leptons, 63% for up quarks, and 94%, close to maximal, for down quarks, including the bottom quark, which you can pick out explicitly. You can also get information about this from unpolarized beams using the forward-backward asymmetries. Here is the formula. And maybe I should just say that this striking pattern where the parity asymmetry varies dramatically from leptons to bottom quarks is seen in the experiments. There's a huge literature on this. I hope Alain will cover it tomorrow. This is one little piece of it. The tau, in its decays, analyzes its own polarization. There's an explanation for that here that you folks can study offline. If there were no parity asymmetry, this is the energy distribution of the pion in tau to pi nu. If there were no energy asymmetry, this would be flat. The contribution from a left-handed tau looks like this. The contribution from a right-handed tau looks like this. A good theorist can infer that from the explanation here. I leave it as an exercise to the students. You can see that a 15% asymmetry is just about right, and that's also more precisely what fits the data. This is a small asymmetry. On the other hand, for bottom quarks, there's a characteristically large asymmetry. This was measured at SLAC using polarized electron beams, essentially using the fact that left-handed electrons produce forward left-handed Bs, and right-handed electrons produce backward left-handed Bs. So if the asymmetry is maximal, what you expect is that a left-handed beam will produce a completely forward distribution, and a right-handed beam will produce a completely backward distribution. Well, here's the data, and it's really amazing. It doesn't go to 0 here because of your imperfect ability to discriminate Z's from B bars, B's from B bars. But a maximal asymmetry, or one very close to maximal, fits this data extremely well. Okay. Now, for a full accounting, there's one more important effect that has to be included. The top quark corrects the difference of the W and Z vacuum polarizations by an effect proportional to mt squared over mw squared. And the Higgs boson also contributes to this quantity with an effect proportional to the log of the ratio of m Higgs squared over mw squared. This is a relatively small effect, but this one is absolutely essential. If you don't get that right, you can't make a correct comparison of theory and experiment. And that meant historically that the LEP experiments could predict the value of the top quark. Now, different people feel differently about this. Bryan feels very strongly, and I encourage you to look at what he says in his article. Here I'm taking a somewhat weaker point of view, that one never really had a precise evaluation of the top quark mass in advance of the CDF and D0 discovery of the top quark. But certainly you had an indication that the top quark was in this region before the top quark was observed at the Tevatron. So here is a 1993 Aleph result. MT equals 156 with some large errors, which has to do with the fact that you're looking at an order alpha correction to the precision electroweak. So the correct value, of course, is about 172, and it's right in that window. The large top masses required in some theories of the Higgs sector, in particular the Bardeen-Hill-Lindner theory, which was popular at this time, were also excluded by the fact that the upper limit here. Actually, when I explained this at the time to Sid Drell, that we knew that the top quark mass was below 200 GeV, he said to me, "Put your money where your mouth is." And very nicely, he paid off with dinner for 4. That bet is recorded in the Slack bet book. Okay. Here's a more current rendering of that. So the blue contour this is the M top versus M Higgs plane, assuming that the standard model is exact. The blue contour is the area enclosed by the precision electroweak radiative corrections. You can see that it actually prefers top quark masses in this high range. So this uses the complete set of LEP data, doesn't include the Tevatron top quark mass determination. That would be given by this line here. And at the time this was done, July 2011, this region here had been excluded by LEP. So you can see that there is a good rapport between electroweak and the direct measurement of the top quark mass. You can also see that the rapport works only if the Higgs is relatively light compared to its full range. It has to be near 100 GeV. And this is the basis for the statement that precision electroweak actually told us that the Higgs must be a light particle below the W threshold, and in fact quite far below the W threshold. So that's the contribution of precision electroweak, somewhat in advance to our understanding of the top and the Higgs masses. This slide shows the status of the precision electroweak experiments as of the final review in 2006. Let me just pick out this number here is the RB that I highlighted. Here are various flavor asymmetries. This is compared to a fit, which is the best set of standard model parameters that fits the corpus of data. The little bars here show the pull in the error divided by 1 sigma. You can see that the value of the top quark mass at this moment, 173 would put it somewhat on the other side, is in very good agreement with this corpus of data. Okay, I'm almost done. I think I can't leave the subject without talking about one more precision calculation and its rapport with experiment. And that is the process E plus E minus to W plus W minus, which was also studied at LEP at the highest energies. It was known that this process was extremely interesting because if you calculate, for example, this diagram, which was already done in the 1950s, one discovers that this diagram has bad high-energy behavior that violates unitarity. After the invention of the SU2 cross U1 model, and actually in the late 70s, Alice, Boyer, and Bourras calculated the full set of diagrams at tree level in the Weinberg-Salam theory. And what they showed was that the bad behavior of this diagram is exactly canceled by the bad ultraviolet behavior of these diagrams, provided explicitly that the vertex that appears here and here has exactly the form predicted in Young-Mills theory. Any deviation from that form, and the theory goes haywire. It was wanted to test this prediction precisely at LEP2 at the highest energies near 200 GeV. The radiative corrections to this process were first calculated by Bohm, Denner, Sack, Bienacker, Behrens, and Gif. Essentially, this was, I think, really the hardest precision electroweak calculation done in the era of the late 80s. However, it was then realized that one had to do something even harder, because actual W bosons are not stable particles. They're produced off their mass shell and decay. The off-mass shell Ws interfere with other processes that just basically give random methods for E plus E minus to turn into 4 final state fermions. And those all have to be accounted and interfered with these diagrams correctly to get a sub 1% accurate theory. So this was done in the 90s, first by Kleiss and others inventing the phase-based generators that were actually capable of producing these reactions, and then one actually had to calculate all the amplitudes. I think the first time it was done was in something called the Raccoon event generator by Ansgar Denner, Stefan Dittmeier, Marcus Roth, and Doreen Vakarot. I don't, unfortunately, have a picture of the whole calculation, but Doreen was the graduate student who did the heavy lifting, so her picture should stand in for it. In any case, the calculation, and maybe I should say a parallel one done by Benny Ward's group, really fits the data extremely well. So here are the LEP2 data points, the average of 4 experiments. The blue is the Raccoon and YFSWW. That's Benny and Stanislaus Monte Carlo. And this is the result of leaving out some diagrams. And you see the theory goes totally haywire if the vertex is not exactly the Young-Mills vertex. So again, a very remarkable vindication of the standard model, and one I think that this is really underappreciated how powerful this is, and people should appreciate it properly. Okay, that's what I wanted to say. The standard model is understood now to very high precision, below 1% for all important observables. It passes many qualitative and quantitative tests. Even the qualitative tests I've emphasized are very non-trivial. So this theory is really amazing. It works fantastically. And I ask the question here, shouldn't we believe it is exactly correct? Of course, that's a setup for the next talk. But let me end this one and take any questions. Thank you very much.
The forward-backward asymmetry from SLAC always used to stand out a little bit in terms of pull. You showed it also. Of course, measuring so many parameters, 1 or 2 have to stand out. But if you would want to look for a hint, there are not too many places where we can look. Would there be a natural way to incorporate that as a physics hint, or really we are required to leave it as a standout?
So what you're discussing is this measurement, which as you see is close to 3 sigma discrepant, and this measurement, which actually is close to 1.5 sigma discrepant from the standard model, and actually the discrepancy is really in the other direction. This is the absolute value of the pull. So these two measurements, when compared to each other and ignoring everything else on this slide, are discrepant by, I think, about 4.5 sigma. It's a substantial effect. I think the AL-SLD is in quite good agreement, though, with other determinations. So the sign of the discrepancy is the same for this, for the tau polarization, and for the leptonic forward-backward asymmetry. If you ask me, it's really kind of a hadrons versus leptons effect. I have a theory that blames LEP, that this measurement is completely wrong. My LEP collaborators, whenever I mention this, pour anger over me, so I'm not going to mention it here. In any event, that little discrepancy in this whole table, I think, is, it really is just one thing sticking out as the result of statistical error. One thing that I should say, though, is that let me go back one more slide. So I told you that the AL here and the sine squared theta W is basically determined by this factor, with the AF being maximal. And so one has a lot of trouble making a theory in which AFB is different from AE without having this number be different from maximal. And as I told you, the maximality of this factor is actually independently tested. So it's quite complicated. There are papers on this, but it's quite complicated to make a theory where you make all of these things consistent. And most likely, either it's statistics or somebody made a tiny mistake. I should also notice that these numbers don't represent the accuracy of the experiments. This one, and this one are among the numbers here, as you can see in the column, with the smallest stated errors. And so, if someone estimated their errors a little, you can bring everything into reconciliation. I think Alain will talk tomorrow about the possibility of an extended statistics Z program that could probe this issue. I probably should also say that experimental anomalies should be vindicated by theory, and there's no good theory of this, so please excuse me.